Hey, all. Today we are going to shift our discussion from confidence intervals to hypothesis tests. They're similar. In a hypothesis test, we are going to use information from a sample, much like we did with a confidence interval. But for a confidence interval, we were trying to capture or estimate using an interval parameters like a population proportion or a difference in two proportions, a population mean, a difference in mean, and in the most recent case, using paired means. For a hypothesis test, what we're trying to do is use sample data to see if we can justify some sort of claim. We are going to be doing we're going to go through the same parameters. So we're going to start out with a hypothesis test for one sample proportion. A lot of the things are going to be very similar. We need to justify by doing assumptions and conditions. We need to do some calculating, which we can do on the calculator. And then we need to draw some conclusions, much like we did for confidence intervals. Obviously, there are going to be some differences, so make sure you pay attention. So we had intervals before. Now we are testing hypotheses. It's a bit like if you could imagine a court case. There are two options at the end of a court case. You can either be found guilty or not guilty. And the one thing we always do, or we're supposed to do, is we're supposed to start with some assumption of innocence. So when somebody goes on trial, we start by assuming that they are innocent until we collect enough evidence to say, well, hang on a second, they are not innocent, they are guilty. So we start with hypotheses. When we do a hypothesis test, there are two. This first one, H sub 0, is called the null hypothesis. The null hypothesis is the thing at the beginning of our hypothesis test that we are assuming is true. So in this case, we're talking about population proportions, P. Remember, P hat is a sample proportion. So whenever you see P hat, that has to do with the sample. P, just regular P, that has to do with the population. And then this P sub 0, that is our hypothesized proportion value. This HA, this is an alternative hypothesis. Much like in a court case, we assume innocence. That would be our null hypothesis. We are looking at evidence to decide whether or not it's plausible for that person to be innocent or not. And the alternative would be that they would be guilty or not innocent. And if you see here, our null hypothesis is inequality. We're saying, hey, look, we are assuming that the population proportion is equal to this value. Our alternative is always going to be some inequality, greater than, less than, not equal to. Something that is different from being equal. And so in order to make calculations, we use the distribution of sample proportions. And so the mean of that distribution in this case is going to be the assumed null proportion. If you notice here, some differences than when we did confidence intervals. When we did confidence intervals, we had P hat and Q hat. This time we have P0, Q0. So just be careful. Those little notations that don't seem important are very important, so that we're using the correct values when calculating these measures. So we have the same assumptions and conditions that we did for a confidence interval for one proportion. We need a random sample. We need independence. That means our sample must be less than 10%, or we need to know that each individual is independent of the other. And we need to be able to justify using a normal model, the distribution of sample proportions as an approximately normal distribution. So we need our NP, our number of successes, and our number of failures, NQ. And remember, we're using from our hypothesized value, um, we want to know, hey, if this hypothesized value is true, will we have the requisite number of successes and failures greater than or equal to 10? So same thing to check, just got to make sure we use the correct value of P. Don't use the sample proportion, use the null proportion and then the null Q. As always, if you have questions about these little tiny details that are very important, make sure that you ask. And hopefully maybe doing a problem will help clear some of them up too. So go ahead and take a look at this question. This is in the PDF of the book as well, number 15. So if it's easier to see there, just go open that up, take a look at this, and then we'll do a hypothesis test together. So we are looking at elementary school statistics, and in particular, we're looking at absenteeism. And they're using these 1996 numbers as a baseline. So this is what we would assume to be our population proportion. And then they took a sample in the year 2000 and a randomly chosen sample, and they got a sample proportion of 33%. So what I do want to document right away, right up front before I start doing anything, is what are my values. So my P0, the thing that we're assuming is the population proportion is 0.34. And so Q0, we just subtract that from 1 and we get 0.76. I'm sorry, 0.66. This 33% comes from a sample. So that is a sample proportion. So that is a P hat. In this case, we don't need Q hat. So this is a really good way to document what we have so that when we go make some calculations, we are using the right value. And these are very close, so they will get you similar results, but not exactly the right results if you use the wrong one. So we need to, first, we're going to start by writing hypotheses. So we need a null hypothesis, the thing that we are assuming is true. Right now we are talking about population proportions. So we have something that we assume is the population proportion, and we want to see if that's still the case. So we are going to say P is equal to that 0.34. And we want to know if there's evidence of a change in student attendance. So a change indicates not being equal to what we thought it was. It doesn't necessarily mean it gets greater or smaller. What we want to know is, did it change in some way? So we are going to say our alternative would be that our proportion is not equal to 0.34. This symbol, even though it seems like it may not be super important, becomes very important when we run the hypothesis test on the calculator and we make calculations. So just make sure that you're practicing getting the right one. If I said, is the proportion less than what we think it is, we'd put a less than. Is it greater than? We'd put a greater than. Some indication that that's what we're looking for. But right now we're just looking for a change, which usually indicates we just want to know, is it different from what we thought it was? Not equals to. We need to satisfy assumptions and conditions. The first one is random, and I am going to not write them all out today, but you should be writing them all out. This is something we've been doing now for a few weeks, so hopefully you understand that's true. We have a randomly chosen students, so we have randomness. 8,302, that is a lot of students, but in elementary and secondary education in the United States, that is certainly less than 10% of all students, and so we should have some independence. And the last thing we need to check, which I will write out, is we need to check our NP from our null. I'll call it NP null and NQ null. So we are going to multiply our 8,302 by our null P and by our null Q. And what we're saying is, since we're assuming that this is true until we can show otherwise, then we are going to see, hey, if this is the true proportion, will we have enough successes and failures for it to apply to the normal model? So let me make that calculation. And you may have noticed I wrote the wrong Q down. It should be 0.66. I did P twice. So our expected successes and our expected failures far surpass the minimum requirement of 10. So we're good. We have randomness, independence, and we have NP and NQ greater than or equal to 10, so we can use the normal model. We have our hypotheses, so now we need to do a test. And so what we do when we get a test is we are going to find what's called a p-value, and we find that p-value, it's on a normal curve. It's measuring the area underneath the curve. So when we have a greater than or less than, we're getting what's called a one-tailed p-value. It's looking at either the right or the left tail and telling us how much area is there. When we have a not equals to, it's a two-tailed test. And so it is going to give us the area underneath both tails. And so it's very important that we know if it's one-tailed or two by knowing the correct alternative inequality. And so we are going to run, we're going to run a one proportion z-test, and that is stat tests and so we're going to use some notation here. I want to know the probability that my sample proportion is, I'm sorry. Since it's a two-tailed, we're going to multiply it by 2. The calculator will do it for us, but we want to write the notation correctly. We're going to double the probability that our sample proportion is greater than 0.34. Greater than would be the right side, less than would be the left side. So that's why we multiply it by 2. So we want to know what is the probability if our true population proportion is 34%. What's the probability that we get a proportion of 33%, our sample proportion? Again, these little things are very important, and if you need me to re-explain, please ask for help. No problem with that. So we'll do our one proportion z-test. We're going to tell it our null hypothesis p, which is 0.34. We are going to, n is our 8,302. Oops. X that we get from multiplying 33% by 8,302. That's the actual number of people who said they were chronic absentees. So I can, in my calculator, do 0.33 times 8,302. It's not going to like a decimal, so I'm going to round that to 2,740. You're going to choose your correct alternative. We have a not equals to, so that's good. And then we can calculate. In class, somebody remind me, I'll show you what happens when you draw. And so we get some information. It gives us a z, gives us a p, it gives us a p hat, and n. So p hat is our sample proportion, that 33%. P is a probability. This is the answer we're looking for. So 0.055. So what this probability means, this is really important. What this probability means is if our actual population proportion was 34%, there is about a 5.5% chance of getting the sample proportion we got. So if the true population is 0.34, then there's a 5.5% chance that we get the sample results that we had. And so what we need to do is decide is to make this conclusion. And so at this point, I think what we're going to do is we are going to just get to this point, and then in the next lesson we will talk about what sort of conclusion to draw. So the important thing to take from this lesson is writing your hypotheses, doing your calculation on the calculator, and then getting your p-value. So this is a p-value. And a p-value is a probability. So in the next lesson, we will discuss how to interpret this p-value, what we do with that p-value, and potential errors that we can make in our hypothesis test. So for now, getting used to writing the hypotheses, making the calculation, justifying using your assumptions and conditions, and then getting the p-value. So I do have a problem for you to answer some questions on. As always, if you have questions, please make sure that you ask. Please make sure you do some practice to get better at this part so that when we get to the next step, you'll be ready to go. I ran a little long today. I apologize for that. Hopefully it wasn't too bad. Make sure you answer the questions and ask for help.